Welcome back to the Causal Inference Seminar. So we did this last spring, and for this spring, we're going to kind of have this marathon day of 2 talks on causal inference techniques. And at the Salem Center, we value diversity of viewpoints. So we're first going to have a frequentist speak. This is Sam Wang right here, and then we're going to have a Bayesian talk at 4 p.m. today. So Sam and Ken, both of the speakers today, I did a postdoc with at the Booth School of Business. They're both great friends, and they both do very interesting work on causality. So without further ado, Sam, welcome.
Yeah, thanks. Thanks for your patience. I grew up in Dallas, and so actually most Saturdays in the fall, I was actually glued to the TV rooting for the Longhorns, and so it's really nice, I think, to be here on campus and to be able to talk to y'all about some work today. Okay, so before I jump in, just want to note that this is joint work with Lon Kolar, who's at the University of Chicago, and Matthias Sturton, who is at TU Munich. All right, so this is the Causal Inference Seminar, so maybe I don't have to sell you too hard on why causality is important, but I do get questions often about why do we care about causality when we have a lot of these really complex, very, very impressive in many ways, black box predictive models, right? And so I think obviously from my standpoint, I think kind of the quest of science is all about discovering causality. But even beyond that kind of intrinsic satisfaction of learning causal relations, the big advantage that I think of having a causal model and not just a predictive model is that causality allows us to reason about interventions, right? So this is particularly important for things like public policy here at the Salem Center. So here's just kind of a toy example. You might have seen this before. It's from the New England Journal of Medicine in 2012. And so we can see that on the horizontal axis, we have a chocolate consumption per capita. And on the vertical axis, we have Nobel laureates per capita. And each of these points represents a specific country. So we can see here that the correlation is actually quite high. It's a correlation of roughly 0.8. And so if we have chocolate consumption per capita, we can predict the Nobel laureates per capita pretty well. Okay, so say you're Jay Hartzell and you see this, right? You're evidence-based, right? What do? Do you force people to start eating chocolate to increase research productivity? I saw that David had a big thing of chocolate in his office. I don't know if that's related to this at all. Or maybe you're an executive at Hershey's, right? Do you start funding basic research here in the United States to increase chocolate consumption? Right? Both of these questions, right, are questions not about the current state of the world, but as a question about an intervention, right? And so, in order to answer any of those questions, we need not just associations, but we actually need a causal model. Okay, so this is another kind of example that might come up, and this is in some sense the canonical example of what we might do with causal discovery. So causal inference is a very broad topic, and I'm going to talk to you specifically about kind of problems in causal discovery. And so what do we mean by this? So this is a protein regulatory network from a paper by Sachs et al. In Science in 2005. And so this is what I'm showing you here is kind of some representation of a system that's happening within a biological cell. And so each of these kind of orange things here represent a particular protein you might observe in a cell. And you can view this in many ways as a directed graph. And you see these arrows here. So for instance, we have an arrow from this protein, PLC gamma, to PIP2. And what this means, or what this kind of picture is encoding, is that PLC gamma has some sort of direct effect, a direct causal effect on PIP2, on the expression levels of PIP2. Okay, so in the paper, this is called the consensus network. And so what this means is that over a series of years, a bunch of grad students were sitting at a bench with a bunch of pipettes and beakers doing a lot of experiments. They got a bunch of information that was published in papers, and over time, all of those papers, all of that knowledge coalesced into this network that we have here. All right, and so causal discovery basically asks the question, given observational data, can we select a causal model which generated the data? So put another way, in this specific application, if I just had single cell data, right? So instead of doing an experiment, if I just observed a bunch of cells in the wild and I got the counts there, could I get a good guess at what this network looks like? Okay, so obviously experimentation is the gold standard for determining causal relations, and so if we can do experiments, this is ideal. But there are many cases which experiments are either too expensive, infeasible, unethical, or perhaps just the search space is too large. And so you want at least some sort of exploratory estimate of what your causal structure might look like. And so this is exactly where kind of causal discovery comes into play. All right, so throughout this talk, I'm going to be using the language of graphical models to talk about complex systems. So in particular, I'm going to represent a system with a graph where I have a set of vertices, V, and a set of edges. And each vertex in my graph represents a variable that I've observed. And each edge represents a dependence relationship. So for instance, in this case, if I have an observation in R4, so I have a vector with 4 elements, I have 4 variables that I've observed. I have a graph with 4 vertices. And the way that I'm going to encode causal structure is with these directed edges. And so in particular, if a node has a direct effect on another node, then I'll put a directed edge between the two, and I will say that the cause, in some sense, is a parent of its child. So in this case, Y1 has a direct effect on Y3, and we're going to say that Y1 is a parent of its child, Y3. Similarly, if there's a directed path between 2 nodes, then we'll say that the cause is an ancestor of its descendant. So in this case, Y1 has a series of edges to Y3 to Y4. So we'll say that Y1 is an ancestor of its descendant, Y4. Okay, so we're going to assume, this is an assumption that we will make, and this is a quite common assumption, that the causal structure that we're trying to recover corresponds to an acyclic graph. And so what we mean here is that you can't follow a series of edges and get back to where you started, right? So there's no feedback loops. If this is true, then we always have at least one causal ordering of the nodes. And what we mean by this is an ordering of the nodes where the variables which are earlier in the ordering are not an effect or not a descendant of nodes which come later in the ordering. So basically, you can think about this as kind of ordering the variables in some sort of causal ordering. Okay, and just throughout the talk, I'm going to use PA of V, DE of V, AN of V, and ND of V to denote the parents, descendants, ancestors, and non-descendants of V. So just a little bit of notation. And then finally, given some sort of ordering theta, I'm going to use PR theta of V to denote the variables which precede V in this ordering theta. Okay. Are there any questions there? Yeah.
Yeah, can Y1 affect Y4 independently of Y3?
Yep. So in this case, the way that we've drawn the graph implies that does not happen, okay. But you can certainly have a graph which includes this edge.
Yeah, I just asked specifically about that. So it's all the influence that Y1 has on Y4 is through Y3. That's correct. Okay.
Yeah, that's what this. Yeah, that's what's encoded in this graph. That's right. Yeah, and so of course this is. Feel free to kind of jump in and ask questions throughout. Yeah, this is meant to be very important. Okay, so in causal discovery, there are kind of generally, at least, well, I'd say for the past kind of 30, 40 years, people have been working on this problem. And there's generally kind of 2 steps which people think about. So the first one is one of identification. And so the question here is, what do I need to assume about the class of models that generated my data? so that I can pick out the correct causal model given population values, right? So this is in many ways just a mathematical exercise. I'm going to write down a model, and I'm going to see if I can identify that model from a population distribution, right? And so the game that people play here is that you need to assume a class of models which is small enough, in some sense, that you can identify that model, but you also want it to be large enough to where it actually kind of captures plausible dynamics which are happening in your data, or plausibly captured. Okay. And I'll talk in a few slides about particular identification assumptions that people make. All right, so once you've answered the question of identification, the next question that naturally arises, okay, is one of consistency. So you tell me if I have population data that I can recover the graph, the causal graph. Now, what happens when you give me data? Can I give you some sort of guarantee for recovering the true structure if I have enough data? Okay. And so by and large here, procedures take in data as an input and they output a single point estimate of the causal structure. And so sometimes this is a single graph, and sometimes this is a kind of a broader equivalence class of graphs. And I'm not going to get into that today, but you can think of that still as a single point estimate of causal structure. Okay, so I'm a statistician, right? So identification and consistency is great, but the next natural question, which really hasn't been thought of much in this causal discovery literature, is one of uncertainty, right? So great, you give me data, I can output a point estimate of the graph, but really I want to know something about the uncertainty of that point estimate. Okay, so how much confidence do we have in the estimated causal structure? And you know, obviously, as you know, right, the estimated causal structure can be incorrect for a variety of reasons. Perhaps there's just sample variability. Perhaps we've made an identifying assumption which is incorrect about the actual data generating procedure, or maybe there's both, right? And so when I think about uncertainty, I actually want to have some way to kind of reason about these questions.
Yeah, those are incredibly different sources of variability and uncertainty, right? One,
yes,
which I believe that under the assumption of identification consistency, you have sample variability is something that I have a shot at.
Yep.
The incorrect assumptions that go back to the top, those are going to be much harder.
Yes, agreed. Yep, agreed. Okay, so the canonical example that I showed you was one of a biological network, where in some sense we don't know what the treatment is and what the effect is, and that's kind of what we're trying to target, right? In a lot of policy questions, right, there are actually clearly defined treatment and clearly defined outcomes of interest, right? And so perhaps you're asking the question, well, I get that this is relevant for biology, but why is this relevant for questions of policy? And so hopefully what I will convince you of on this slide right here is that actually there are still a lot of kind of interesting questions that this kind of work will be able to answer for questions of policy where you do have a well-defined treatment and well-defined outcome. So say you're using a regression-based approach to adjust for confounding, right? You're just going to use regression to estimate some sort of causal effect, right? So kind of the most natural thing kind of we can think about here is that we need to adjust for confounders and or mediators in order to recover a causal effect, right? And so the kind of the naive approach here, right, is, well, if I'm not sure if something is a confounder or not, I'm just going to throw it into my regression and, you know, just to be safe, right? So I'm going to include as many confounders, even if I'm not sure, you know, subject to having enough samples, right? So subject to kind of being able to actually kind of get good, precise estimates of that. Okay, so I called it the naive strategy, right? Which kind of like maybe is a little bit telling. And in fact, this is actually not a good strategy in practice, because conditioning on variables which are downstream of the outcome can actually yield biased estimates of the causal effect, right? And so in kind of there's this tension where if you don't adjust for enough variables, you can be biased, or you can get biased estimates of your causal effect. If you control for too many variables, or if you control for the wrong variables, you can also get a biased effect. So it's not, in some sense, there's not kind of some sort of monotonicity property here where you just control for as many confounders as possible. So here's just kind of a toy example here. So say I'm interested in thinking about the effect of tutoring, some sort of maybe after school tutoring program. That's my treatment of interest, and my outcome of interest is grades. So we're thinking of maybe high school students, and we want to ask the question, should we increase or should we maybe require students to attend some sort of after school tutoring? Okay, so we think, and maybe we have kind of one covariate which we could include in our regression, and this is whether the student kind of participates in athletics or not, or kind of maybe to the extent which they do. Okay, so one plausible story for this is that going to after-school tutoring actually restricts a student's ability to participate in athletics, and so maybe that there is a directed edge from tutoring to athletics, and maybe athletics has a causal effect also on the outcome of interest grades. Right? And so, this could be positive or negative. I can see stories in both directions, but it's not kind of seems very reasonable to make that assumption. Right? And the actual outcome of interest is represented by this edge here, which is the effect of tutoring on grades. And in this case, if we are interested in the direct effect of tutoring on grades, then we ought to include athletics as in our regression as a mediator. Okay, but let's say that this is actually the causal structure, right? So here I flip this edge where actually, and I think this was true when I was growing up, and I think it's still probably true. If you fail a class, or if you're close to failing a class, you're actually prohibited from participating in athletics, right, in the state of Texas. And so maybe actually it's the opposite direction, where we think that the outcome grades actually has a causal effect on whether a student participates in athletics. In this case, athletics is what's known as a collider. And if we then include athletics in our regression, we actually get a biased estimate of this causal effect here. Okay, so if we're trying to estimate this causal effect, and if we're trying to get any sort of uncertainty about that causal effect, our uncertainty about the causal effect should actually encode any uncertainty that we have about the actual causal model as well, right? And so in this sense, we're talking about what kind of the uncertainty over what is my adjustment set. What do I include? What are the other covariates that I include in my regression? And what I will talk about is kind of primarily the aim of this work is to think about confidence statements for causal graphs, but as a byproduct, as a kind of a very natural byproduct, which I'll talk about, we can also for circumstances like this, where we have a well-defined treatment, well-defined outcome, we can also get confidence intervals for causal effects, which account for model uncertainty about what adjustments, what my adjustment set should be. Okay, so confidence intervals or causal effects should account for uncertainty about the adjustments. All right, I'm going to pause here for a second. Are there any what questions do y'all have?
So in that example you're setting up basically the notion that the uncertainty on the causal mechanism here is where the errors are pointing out. Are you going to consider that, but also the existing variables that may or may not have errors, and or there are other variables in the world, right?
Yeah.
Some of them might have errors and they might not have. So you're also going to have that situation. You might have a bunch of variables that are given to you in the system, but they're not actually at all related. Those are the two sources of zeros in the network.
So we'll need to make a few assumptions, and so we will consider the case. So kind of in some sense, at least this work here, will be a little bit myopically focused on the variables that we observe. So this is certainly the case where oftentimes there's variables outside what you've observed that have some sort of influence. I
was thinking about this, things that you observed just might not be related at all. Maybe just
yes,
there. Okay.
Yeah, and we can allow for that. Yeah, that's right. Yeah, so we have this arrow here, and we're trying to find in some sense the effect of tutoring on grades. but it could be that the effect is 0, right? And that is also allowed by our law. Okay, so I'm going to talk to you about confidence sets for causal models. And in some sense, the uncertainty over model selection may not be, maybe if you're a Bayesian, this is quite natural. For frequentists, this is actually a little bit of a weird kind of thing to think about. But we all kind of know well, or I hope we know well, kind of confidence intervals in a regression standpoint, right? So I'm not even talking about causality. I just fit a regression and I want some confidence interval for a coefficient that I've estimated. And so we have this kind of very mechanical definition, right? At least the frequentist definition, which is, I have some procedure, which if I repeat this on fresh data, right, will capture the true parameter of interest 95% of the time, or 90% of the time, right? But beyond kind of that very mechanical definition, what do we actually do with this confidence interval? Like, what is kind of qualitatively, if we want to think about confidence statements for graphs, what are kind of the key notions that we should capture, which we use when we have a confidence interval for a kind of a regression coefficient? So I'm going to point out maybe two, which I think there are certainly others as well, but kind of the two big ones are maybe the first question: what are other possibilities for my parameter of interest that are not ruled out by my data? Right. So you look at the confidence interval, you see what other values are included in the confidence interval. And this is a related question, right? But the question of how trustworthy is my point estimate? If your confidence interval is very wide, right, like modulo kind of the scale at which you're measuring things, right? But if your confidence interval is very wide, you generally have less confidence in your particular point estimate, right? And so this question of these are kind of two broad questions that you might try to answer with a confidence interval for a scalar value parameter. And these are things that we want to also answer when we're estimating a graph.
By the way, welcome to Life of Bayesian teaching frequency statistics to graphs. It's exactly what I try to tend to think about. Look at a confidence interval. I don't give it the formal definition. It's absolutely useless for their usage, right? This is the way. Okay, those are two statements that they internalize. They make good use of this stuff, right?
Teaching regression this semester, and it's a nightmare.
Yeah, don't teach the formal thing.
Okay, so what has previously been done in this area? So previous procedures consider uncertainty over the parameters or the presence or absence of a specific edge when the causal ordering is known or can be consistently recovered. So in some sense, if you tell me an ordering of the variables, this boils down to so that then you kind of extract yourself out of a causal framework, and it really just boils down to regression, right? So then it is uncertainty over regression parameters. Okay, so we want to actually consider a problem that's a little bit even upstream of that, and we actually want to consider uncertainty over the entire causal structure itself, not necessarily just the causal parameters, right? And so what this means is we actually want a uncertainty set over causal orderings, right? So we're not going to assume that you can recover the causal ordering with high probability or with probability going to 1, which is what previous works have done. Okay, what questions do y'all have? Okay, so a few slides back, I told you that there are cases in which we can recover a graph from observational data, right? And so what I'm telling you is that I can tell causation and not just correlation, right? In certain circumstances, right? And so if you haven't seen this type of work before, I understand it can feel a lot like science fiction, right? But what I want to show you is that this is actually, we're not getting anything for free, right? We're actually getting this from making strong assumptions. And the question that you ought to ask is this assumption that we're making, or are the assumptions that we're making, are they reasonable for the data that I've observed, or the system that I'm trying to model? And so one kind of very common assumption that people make in this area is that of a structural causal model. And so in particular, I'm going to be talking today about a linear structural equation model. And what we mean here is each variable that I've observed, so YV, is a linear function of its parents plus some additive noise term. So this is a pretty restrictive model in a lot of ways, right? But it is also a model that's very commonly used across a variety of social sciences as well as physical sciences. Okay, so the two big assumptions here that we're going to assume that YV is a linear function of its parents. So this linearity assumption, we can relax this assumption. I'm not going to talk about that in this talk, but in some sense we can. It's very natural to relax that assumption to just an additive, general additive model. But the big assumption that we make is that there's no unobserved confounding. And so the way that we encode this assumption is that these epsilon v terms are independent across each of my elements, right? So Carlos, in the case you had mentioned, if there is some sort of unobserved confounding that is like kind of outside of my system, then you might expect these epsilon terms to actually be dependent. But we're going to make an assumption here to start that doesn't occur. Okay, so under this model, Shimizu et al. In 2006 show that the exact graph can be recovered from population values when these error terms are not Gaussian, right? So this is a little bit unintuitive, right? Because we're scared of data that's not Gaussian. But here we actually can see that, at least this claim, is that having data which is not Gaussian is actually beneficial for us. And like I said earlier, the identification also holds in nonlinear additive models. And our procedure kind of naturally generalizes to that, but just kind of for the sake of time and clarity, I'm not going to go into that right now.
So PA of V is identifiable. Assumption of linearity.
Yes, that's correct. Mm-hmm. Yeah. So in some sense, what this means is if I have some graph that's generated my data. So let's go here. I can tell you under this in a population setting, I can tell you not just where the edges in my graph are, but the actual direction which they point. Yep, that's right.
That's methodical.
Yeah, under this assumption of non-Gaussianity. Okay, so why is this actually helpful? Right, so let me give you a small proof by example, and then I'll hopefully this kind of drives a lot of the intuition. Okay, so I'm going to think about bivariate data, P and C, where kind of just by notation, P is a parent of its child C. In this case, both of the errors are drawn from a uniform distribution with variance 1. And I wanted to guess. I'm gonna have two hypotheses. Either P is a parent of C, and this is the graph that generated my data, or C is a parent of P, and this is the graph that generated my data. So I'll say this one is the correct one, and this is the incorrect one. But let's see how we might be able to find that. On the left-hand side, okay, well, I should say in both graphs, actually, what I've done is I plotted what I think is the parent onto what on the horizontal axis, and what I think is the child on the vertical axis. So if you just stare at both of these plots, it's a little bit difficult to make any sort of distinction between the two, right? Why you would pick one model over the other is not so clear. In the red, I fit the regressing the child onto the parent, or what I think is the child onto what I think is the parent. Okay, so now what I've done here is after I've done this regression, I can look at the residuals from that regression. And here I've plotted these residuals on the vertical axis, and I've plotted what I think is the parent on the horizontal axis. So on the left-hand side, where I've correctly specified the linear model, or the causal model, sorry, I can see that the residuals that result from the regression are actually independent of the parent, right? So you can look across the range, and there doesn't seem, the distribution of the child doesn't seem to differ depending on the value of the parent. On the right-hand side, I can see that the residuals are uncorrelated with the parent, and this just comes from the first order conditions of least squares. but they're not independent, right? And you can see this by just going across the range of what I thought was the parent, and you can see that the support for the residuals changes. Okay, and so the reason why non-Gaussianity is important here is in the multivariate Gaussian model, uncorrelated and independent are equivalent. But this is generally not true when you have non-Gaussian data. And in fact, you can show, and there's kind of statements to the effect that this only holds for Gaussian data. Okay, so that was the bivariate case. And what can we say about the case when we have more than just one variable, right? And so here, if I have a node V and some set U, and these represent variables, I'm going to let dVu be the population regression coefficients of V onto U, right? So this is just the least squares minimizer in a population setting. All right, and so this quantity is well defined regardless of any kind of causal interpretation. We're going to let eta VU denote the residuals when using this population quantity. So we have YV minus dVu YU. So it turns out when U contains the parents but does not contain any descendants of V, in some sense, if we have well specified U, and it turns out that eta VU, these residuals, are independent of the regressors, right? So this is exactly what I showed you on the previous slide in the bivariate example, and it generalizes more or less exactly the same to when I have more than two variables. And roughly speaking, and I'm going to kind of glide over some details here, but roughly speaking, when U is not specified well, in the sense that when U includes some descendants of V, then this independence relation no longer holds. So kind of the statement that we can make is when I have when I've picked the right set U, such that I've included all the parents of some node V, but none of the descendants, this is equivalent, or this implies that eta VU, these residuals, are independent of U. Right? So we can kind of use this statement here as a certificate for checking if I've picked the right set U.
So here you have that identity at the bottom, ND. What ND again is?
The non-descendant.
Non-descendant. Okay, so V is descendant constant. Okay, so you basically stating it.
Yep.
So it's if and only if, therefore, I can check the residuals. They are independent of U, then I know I'm right.
Yeah. Yes, roughly speaking. So the intuition is, yeah, that's right.
I think algorithmically, in trying to find the set of U, if I have all these different variables, I can try different orders.
Yep.
As once I hit that,
yes,
I'm like, okay.
That's right. That's right. Yeah. So if you didn't care about computation, just try any subset you want, and once you get this, get the maximal subset, and you're good to go. Okay. So this is identification. I'm gonna speed up a little bit here, but please do stop me if you have any questions. Okay, so that's identification, and you can also kind of imagine how you would do this, how you would algorithmically form some way to consistently estimate the graph. All right, so how do we then, how do we propose to think about uncertainty for the estimated graph? So we're going to outline what is really actually a pretty simple framework, and in some sense that's a little bit of the beauty here, is that it is a really simple framework. And there's two parts, right? So one, I need to develop a goodness of fit test for a given causal order. So you give me a causal ordering, and I need a asymptotically valid goodness of fit test. And that goodness fit test, I'm just going to say, produces some p-value, which I'll denote pi of theta. Okay. And so what I'm going to do is I'm just going to invert that goodness of fit test to form a confidence interval. So what I will do is I form a confidence interval or a confidence set of causal orderings by considering any ordering theta which is not rejected by my goodness of fit test. Okay, so this is relatively straightforward, but there are a lot of details which become quite challenging, which I'll mention a little bit later. But before we get into that, hopefully I can convince you that this is actually an object of interest, an object that you care about, right? Obviously we can make kind of statements about this particular object, but why do we actually care? So I told you kind of these two questions. What are other possibilities which are not ruled out by the data, and how trustworthy is my point estimate? So these are ideally what we would be able to answer with some sort of confidence set. So the first question, what are other possibilities which are not ruled out by my data? This set is exactly that answer, right? I've done a goodness of fit test using my data, and I've thrown out the causal orderings which are ruled out by my data. And then the other question, how trustworthy is my point estimate? We can also look at the size of this set, right? If the size of your set is very small, then maybe you have more confidence in the actual estimate. But if the size of your set is very large, you know that there are many causal orderings which may have competing causal interpretations. And so the stock that you would put into any particular causal ordering that you get back is maybe not so high. Yep.
So I guess, so theta, how do you think about summarizing them? So I'm trying to visualize this.
Yeah.
Right? So you basically have all these different rankings. Is that kind of what this looks like? So you have all these different orderings.
Mm-hmm. It's just a set of orderings.
So you're mapping a p-value. So it's like a p-value is a function of this like set of orderings. And so how do you even think about summarizing this?
Yeah, that's a good question. So I'll get to that on like 2 slides.
Okay.
Yep. So the first kind of statement we can make about this is suppose theta g is the set of all valid causal orderings, right? So the graph may not have a unique causal ordering, so we have a set here. And if I have an asymptotically valid goodness of fit test, then I can make this statement here where my confidence set here contains a true causal ordering with some predetermined probability. Okay, so this is similar to what you would want out of a confidence set. There's kind of something here that's maybe not as natural, right? We actually can't contain the entire, we don't have an inclusion, we actually just have an intersection. But nonetheless, this is in some ways because we look at orderings where there may not be a unique ordering for the graph. Nonetheless, we look at orderings because it is the set of possible orderings is much, much smaller than the set of possible graphs. Nonetheless, the problem of estimating a graph, given the ordering, as I told you earlier, basically boils down to regression. And so if it is true that given an ordering, you can get the graph with probability going to 1, then we can make kind of the statement that you would want, not about causal orderings, but about graphs. And in particular, we can say something like the true graph is within some sort of confidence set of graphs with some user-determined probability. The other things that are useful about this particular set is that we can get a sub or superset of ancestral relations. So if you think about kind of given the true graph, I want to know for every pair of variables, is U an ancestor of its descendant V, right? And what I'll say here is that you can post-process this particular set to get an upper bound in some sense and a lower bound, right? So these are sets, so they're not necessarily bounds, but you can think of kind of a upper set and a lower set. So this is sometimes, you can think of this as maybe some sort of an envelope of edges that contains the true set of ancestral relations. So this is one way to kind of think about that. You have a lot of different orderings, and how can I kind of summarize this in a way that is maybe gives me answers about certain causal queries you might make. And this is kind of then the question that I showed you at the very beginning. I can also post-process this object to get confidence intervals, which account for my model uncertainty about what I should be adjusting for in the case where I have a specific treatment and a specific outcome. Okay, so the framework that I've given you is actually very simple, and it's just a goodness of fit test that I'm going to invert. But there are many actually challenging details, which is just kind of like form the basis of this paper, right? So the first one is a statistical problem. Can I develop a goodness of fit test for the causal ordering, which produces a valid p-value asymptotically? And of course, the second one is a computational issue, right? Hopefully, if I wasn't selling you too hard, but if you think for a little bit, if I'm going to try to test all causal orderings, I have p factorial things that I need to test. That's not a good idea generally, right? And so we're going to have to address both of these problems if we actually want to get this data happen. Okay, so I'm done at 1. Is that right? Or
Yeah, but you can go that.
okay,
It's flexible.
okay. So I'm gonna run through some details real quick about the statistical challenges and the computational challenges, and then I'll show you some simulations, and then end with a small example on real data. Okay, so what I told you is in the population setting, if I do this regression and I look at the residuals, when I have correctly specified the causal structure, should be independent of the regressors. So this is in the population setting, and unfortunately, it doesn't. And if you were to kind of naively try to test this, though, it doesn't hold when you have sample data, right? So if I have data, I regress YV onto some other set, which I think are the parents. Even if I have correctly specified the set of parents, because I'm estimating this regression parameter and I don't have the true regression parameter, when I look at the residuals, they will always include some term which actually includes the parents. So if I do this test, if I have eta hat here, which are the residuals which I've estimated from data and not from population values, then it is no longer true that this holds, even though it would hold in the population setting. So the way to think about this is that here, the regression parameters are actually a nuisance parameter that I need to estimate, and that nuisance parameter kind of gets in the way of my hypothesis test. So if you naively apply, any sort of non-parametric, any powerful, I should say, test of independence, in this case, you're actually not going to control the type 1 error at your appropriate rate. Okay, so I'll briefly mention what we do here. So we have a residual bootstrap procedure, which essentially corrects for the bias in this test that we incur from having to estimate a nuisance parameter. I'm not going to dive into the details here, but we're not kind of the first people to think about this. There's a number of this is a problem that goes back quite far. But more recently, there's kind of been a flurry of activity here, and in kind of conceptually, you can think about plugging in any of their goodness of fit tests to this procedure. But we think that our particular test has really nice statistical and computational properties. In particular, our proposed test is theoretically valid when P over N is small, or when it goes off to 0. So we allow for P to grow slowly with N. And also, kind of most importantly, we're going to do a lot of these tests, and so we need something that's fast. And so our procedure is 10 to 1,000 times faster than competing methods. Okay, so given a goodness of fit test for a single regression, kind of maybe the natural thing to do then is just to test each level of my causal ordering, get a p-value, and then combine the p-values in some sort of way, right? And that's exactly what we're going to do. So given some fixed ordering theta, I'm going to test this hypothesis here, that the true residuals are independent of what I'm regressing onto. I'm going to get some p-value out of that test, which I'll call gamma theta of v. And then I'm going to finally combine all of those p-values by just taking the minimum p-value. So what we can show is that asymptotically, the way that we've kind of structured this hypothesis test is that each of these gammas is going to be independent. And so we can just treat them as independent and compare them to a beta of 1 minus p minus 1, which is the distribution of the minimum of uniforms. Okay. So just kind of very concretely, what this means is I'm going to test if I have a causal ordering 1, 2, 3, 4. I'm going to test whether the residuals of 2 are independent of 1, produce some p-value. I'm going to test whether the residuals of 3 are independent of 1, 2, and so on and so on. So I'm just going to test this causal ordering layer by layer. Okay, so just to kind of close out this kind of part about the statistical problems, what we can show is that this procedure is asymptotically valid under the assumption that the elements of epsilon are mutually independent. So we're saying that we have kind of don't have any unobserved confounding in our system, right? This is a big assumption that we're making. And also that the errors are sub-exponential. Right? So this is a class of errors which is a little bit heavier tailed than what people normally consider. I told you that each individual test is valid as long as p over n goes to 0. Unfortunately, the way that we've structured this, kind of aggregated the tests, this means that we actually need p to the 4th over n to go to 0 if we want to test the entire order. And what I'll say here is this is actually a trade-off that we make between computation and statistical properties. It's not so hard to imagine a test which gets better rates than p to the 4th over n. But this, as I'll show you on the next few slides, using this kind of piecewise test, which then aggregates at the end, actually allows us to save on computation quite a bit. So this is a statistical computation trade-off that we have made. Okay, but under those assumptions, we can say that the test for any given ordering is valid, yeah, as long as these things hold, right? And so that what that means is that then, at least from a statistical standpoint, this the confidence set that I want, this theta hat, satisfies the statistical properties that I want. Okay, and then in the nonlinear setting, we just use a sieve estimator and we can track the approximation bias. Okay, so computationally, how do we do this, right? So testing all p factorial orderings, that's generally a bad idea. So can we be a little bit more clever about how we do this? The answer here is yes, sort of, right? So what we do is we have a branch and bound flavor of procedure, which allows us actually to cut out a lot of redundant computation. In the worst case, it is actually still an exhaustive search, but what I'll show you in the simulations is that actually in many kind of reasonable situations, this allows for computation which is feasible in not too much time. Okay, so what does this mean here? So I am testing the causal ordering layer by layer, and I'm getting a p-value at each time. My final test statistic is going to be the minimum of those p-values. And so let's say I'm testing the ordering 2, 1, 3, so on and so on. So there's 10 variables in my system, and I want to test this particular ordering. I know the critical value for an alpha equals 0.1 test is 0.0116. So when I'm testing the first layer of 2 and 1, if I get a p-value which is smaller than this critical value, right? So say I get a p-value of 0.009 from that first test, then I don't need to continue down the rest, right? I don't need to test whether 1 and 2 are ancestors of 3, and then whether 2, 1, 3 are ancestors of 4, and so on and so on. right? Furthermore, I can actually automatically exclude all orderings which start with 2 and 1. Right, so this already kind of cuts down on a lot of the computation that I might have to do. And then furthermore, we're going to do this in a way that actually doesn't consider each ordering sequentially, but considers all orderings simultaneously. And so what we mean here is I'm going to first test all incomplete orderings of size 2, and then I'm only going to consider orderings of size 3, which are not already rejected, and then I'm going to slowly kind of build this up. So this actually also avoids redundant computation. Okay, so let me show you a few simulations, and then I'll close with the data example here. So we're considering a linear structural equation model, and we set P is equal to 10. And we're letting N equals 500, 1,000, and so on, up to 5,000. So I'm generating a random graph with an edge pointing kind of downstream with probability 1/3. And I've drawn the edge weights in a particular manner. And the errors that I'm going to consider, we need this to be non-Gaussian, right? And I'm going to consider gamma, Laplace, log normal, uniform, and y. Okay, so these are the results of the simulations, and I want to just point you through a couple of these panels here. So this panel right here, the left, top left, is the proportion of times that the point estimate, so you use kind of in some sense the state of the art here, the point estimate that comes out, the proportion of times that that point estimate is correct. Right, so we've specifically generated the data in a way such that the point estimate is not consistent. So you can see that it's, even as I'm increasing the size from 500 to 1,000 to 2,500 to 5,000, the probability of getting the correct ordering doesn't really increase, right? And this is just the way that we have chosen the simulation setting. Nonetheless, the size of the confidence set that I'm looking at is still informative, right? In some sense, that we can see that. So on the vertical axis here, I have the proportion of total orderings, total of the 10 factorial orderings, which are included in my final confidence set. We can see that as the sample size decreases, the size of the set actually becomes quite small. So even though I can't consistently estimate the causal ordering, my confidence set still shrinks down as n increases, like you would maybe want. And then in the bottom left-hand corner here, we have the coverage probability. And so the proportion of times that we actually have a causal ordering in my confidence set. We've calibrated these to be 90% confidence intervals, and you can see that the empirical coverage is right around that. Finally, I want to point kind of, in some sense, all of these simulations are for p equals 10, but we can, under kind of certain simulation settings, we can go to the point where we actually consider p equals 20. Now, this is not fast, right? This is roughly 2 days on the Booth cluster, right? But nonetheless, right, if you have an actual problem of interest, right? And so, okay, so when I'm running simulations 2 days, you maybe don't want to wait 2 days for each simulation to finish. But if you have one problem of interest, waiting 2 days is maybe not that big of a deal. Okay, so let me close out with this example here. So I have daily stock return data from French's 12 industry portfolio, and I'm considering daily returns from 2019 to 2022. So N here is equal to 1008, P here is equal to 12. When I use just an estimate of the causal ordering, my point estimate is this ordering here. It's utilities first, energy, manufacturing, and so on. When I form a confidence interval, when I get a 95% confidence set for causal orderings, I actually get a set which is relatively small, and I have basically only one out of every 15,000 of all the kind of the 12 factorial total orderings that I could have. So I have a confidence set that is not actually still large, but it is one out of 15,000 of what it otherwise could be. Okay, so kind of, are there kind of reasonable things that are coming out here? So the first thing that I want to show you here is on the left-hand side. And so I have a set of orderings, and I can calculate a mean of those orderings in some sense. It's like it's a barycenter or it's a Frechet mean. And this basically tells me the ordering that is most like, in some sense, the other orderings in my graph. So I'm not going to dive into the details here, but you can look at the kind of the distribution of distances of each ordering in my confidence set from the mean. And what we see is actually here on this red-hand side, the point estimate is actually on the edge, in some sense, of my confidence set. So my confidence set is actually not centered around the point estimate. And so even though this is the point estimate, it may not be kind of where you most think, where you have kind of most confidence in. It's not necessarily representing causal structure, which you have a lot of confidence in. Nonetheless, what we can see is kind of this set of ancestral relations. We see that in every ordering in my confidence set, we have, and I won't go into the details here, but we have that utilities is first in the ordering, right? And kind of taking this back into the context, what this means is that we think that utilities, or the performance of utility stocks, is first in the causal ordering. So it affects every other industry, but it is not affected by the other industries in some sense, right? I think this may be a little bit unintuitive, but if I show you what we with the time, right? We looked at 2019 through 2022. I don't know if you remember those years. They were some pretty choppy years, right? In terms of the stock market, and utilities are often thought of as a proxy for bond prices. And if we think of bonds as being also some sort of proxy for general uncertainty in the market, right? It then starts to make sense for why we would think that utilities are the kind of the ancestor of everything else, every other industry portfolio. And then finally, I'll kind of end here, but you can also get confidence intervals for each of the kind of the causal effect that we might think of, which account for uncertainty in the ordering. And okay, so this will be my last slide. So we've proposed a procedure which returns a confidence set for causal orderings. The computational feasibility, that is it's a drawback, but it's computationally feasible for medium-sized p. Of course, medium is relative, but what we mean here is roughly 20. We can kind of push to consider settings where p is equal to 20. It allows practitioners to see whether the identifying assumptions used for causal discovery are reasonable. And I didn't really touch on this in the talk, but you can, because we're just inverting a goodness of fit test, you do often, we consider data, which I'm not showing you here, where the confidence set is empty. And what we mean here is that we have rejected every possible causal ordering, and the assumptions we've made are not a good fit with my data. Okay, so the drawbacks are that inverting this absolute goodness of fit test may rule out orderings even when they are helpful. And so what I mean by this is we've assumed a linear structural equation model, which is a quite restrictive assumption, right? It could be the case that the causal ordering is still somehow useful as some sort of projection, but because I'm testing not just the causal ordering, but also the model specification, I could rule that out. So I've listed it as a drawback here, but I think it's kind of both, right? So if the causal, you never really know whether the misspecification is mild enough to actually still have the point estimate be useful, or whether the misspecification is strong enough to actually give you some sort of garbage. And so the fact that we're rejecting it, even though it may be useful as a projection, I think is both a drawback and a benefit. And then finally, this procedure is very computationally intensive, and this is just kind of the way that we've set it up. We're inverting a goodness of fit test. And so there's kind of some of the work that I'm trying to push now thinks about ways in which we can do this, which are not as computationally intensive and allow us to kind of push beyond p equals 20. Okay, so that's where I'll pause, or that's where I'll stop actually.
So we're trying to understand the causal mechanism for distribution data, staring at it, right? Mm-hmm. Through a graph that's a directly synchronous. Typically, you have to try to find that at least through the order.
Yep.
If I handed you a undirected graph for the same data as a starting point,
Yep.
would that be helpful?
Yes.
And because that I wonder if the computational procedure would be tremendously sped up by the fact that we have ways to come up with undirected graphs.
Right.
And if I have a set of those, then all of a sudden maybe there's like some smart things you can do to basically ignore a bunch of
Yes.
orderings that are now kind of ruled out by that association procedure that you get out of an undirected graph.
Yeah. So if you give me the true undirected graph, then it reduces computation drastically, right? Because then I just have to order those edges, right? And then I'm not searching over p factorial. I'm searching over kind of the edges, not quite 2 to the number of edges, but something smaller than that, because Now, the point is to consider uncertainty when I cannot necessarily identify the exact graph consistently. And so you would have to not just give me a specific point estimate of the undirected graph. You would have to give me a confidence set of the undirected graphs. And so if you did this with if I have a confidence set which includes the true undirected graph with 1 minus alpha probability,
Right.
then I do this, then I get kind of coverage with 1 minus alpha over 2, or 1 minus 2 alpha, right? But yeah, that you would have to also kind of have uncertainty for the undirected graph.
But that's something that I think there's a lot of work that's at least, again, algorithmically work that's done to give you the potential to start there. So
Yeah.
assuming that you already have that thing might not be necessarily a terrible thing.
Yeah, that's right.
And then apply what you have downwards, right? Just basically not changing anything you did, just speeding it up tremendously.
That's right. Yeah. No, that's definitely something that you would practically want to look into.
Cool. Thanks, Sam.
Yep.
Thanks, Sam.